Okay, so today we're going to talk about different methods of heat transport, uh, which include conduction, convection, and electromagnetic radiation. Um, I'm probably going to break this up into parts and save most of our electromagnetic radiation discussion for a separate video. So let's go ahead and get started talking about conduction and convection. With conduction, we were talking about heat transportation through direct contact, which we get with a series of microcollisions within the materials involved. Convection involves moving the energy through heat by transporting it with fluid flow, motion of a liquid or a gas, or you could include plasma as well. And then electromagnetic radiation that's light waves or photons. We're not talking about like radioactivity, particle radioactivity, like with alpha and beta decay and that sort of thing. We're talking about, strictly speaking, light. So looking at conduction, I guess let me backtrack for a moment. And for all of these things, we're talking about moving energy from a high temperature thing to a lower temperature thing on average. And in order for this to happen, when this can happen, we are saying that the things are in thermal contact. And I just wrote up there that thermal contact and physical contact are not equivalent. When we are talking about conduction, which we're going to get into again, does involve direct contact, touch. Convection, we're talking about objects that are separated with a fluid medium in between. That is, there's water, there's air and other gases, there's magma flowing below the surface of the earth, there's plasma within the sun, and the heat is moving from one side of that fluid to another and being transported to whatever is on the other side. The fluid's in contact, or in physical contact with all the other things, but the things that are exchanging the heat are not in direct contact. Similarly, we're in thermal contact with the sun right now. We're receiving energy from it, from its light, from electromagnetic radiation, but we're clearly not in direct physical contact. Nobody's touching the sun with whatever. So they're two different things. With conduction, this is sort of like the most obvious experience of heat. And as I've mentioned there, this is basically a series of microcollisions. We remember from when we were talking about momentum and collisions and so on, that when objects interact, momentum is conserved, energy is conserved, the energy can be transferred from one thing to the next. And that's what's going on with conduction. All the particles within the thing are interacting with each other along our object, and with lots of little collisions inside the thing. And that can transport energy that's high temperature on one side to low temperature on some other side. And then if some second object is in contact with a thing, like you're holding on to, I'm in touch with a hot light bulb, and the microcollisions in the surface of the light bulb can hit my fingers and transport the energy that way. Yes, there's also electromagnetic radiation going on there, but let's say we've turned off the light bulb, for instance, and I'm just talking about what's going on from touching with my fingers. And we get that transport while the temperatures are different. It's going on even if the temperatures are in equilibrium, but it's a net zero heat transport at that point. So, like we were looking at earlier, the heat will move until you reach thermal equilibrium, until the temperature is the same. Recall, so. So we can touch a thing, and if we've reached thermal equilibrium, then we're the same temperature as that thing. Different materials are better at heat transport than others. And you may suspect that this is going to be true from what we saw with our equation for heat, where heat is proportional to the temperature change by the thing's mass and specific heat. Objects with low specific heats tend to be electrical and thermal conductors. They have all of these relatively free electrons to carry out a lot of those microcollisions at a more rapid pace than the nuclei of the particles as a whole. So you have metals are good conductors thermally, because the electrons, they have some free electrons that can move around and interact along the way. Insulators with a high specific heat, with a large number for C, tend not to transport the thermal energy quite so fast. When you're in a given room and you're touching various objects in the room will have been in, say, equilibrium prior to your entry. You touch various objects around, like a book, or this whiteboard here, the metal frame of the whiteboard, and your perception of their temperature may be different, even though they all have the same temperature. Because your perception of temperature is based on how rapidly heat is entering or leaving you. Let me write that down. So, if the environment is cold, and you touch an insulator, and you touch a conductor in the same environment, same temperature, the conductor transports the heat more rapidly and feels colder than the insulator, even though they're the same temperature. If you have, if the environment is hot, and you have a hot conductor and a hot insulator that are both the same temperature, and you touch each, the conductor will feel hotter because it is dumping energy into you more rapidly. You only wind up then having them feel the same temperature if the heat transport is the same for each, and that only happens when there's no heat transport at all, if they've achieved the same temperature as you are. That's about all I've got to say about conduction for now. And I think the convection talk will likely be lengthy enough. We're going to break this up and do that as a separate video.